So the first interaction we introduced is called aryl halogenation, and all of the reactions we talk about are going to involve benzene attacking the electrophile to get an intermediate that is no longer aromatic, and we restore aromaticity simply by removing the proton, right? When I make a carbon-carbon bond, the first step is very much like addition to alkenes. I add the electrophile, pi electrons from benzene attack the electrophile, I get an intermediate. Placement of the carbocation is going to be important. Of course, not now because all the carbons of benzene are identical, but we can envision reactions where that might be an issue, and we'll get to that soon. But then, as soon as we make the carbocation, rather than have something else come in and attack the carbocation, which is what we did for alkene chemistry in 351, we're going to simply do elimination chemistry, remove the proton, electrons kick down and restore the pi bond, and aromaticity is restored. So that's the pattern for everything we're going to talk about. Reaction number one is aryl halogenation. We said we need a Lewis acid to kick it up a notch for on the electrophilicity of bromine. So when electrons from bromine donate into an empty orbital in iron, we don't need to worry about what that is. We get a new molecule that's especially electrophilic, and essentially all of this is just a really good leaving group, which benzene can attack to make a new carbon-bromine bond, and then we've got aromaticity gone, which we restore from that elimination step. So that's aryl halogenation, and you can do this with both bromine and chlorine. Your text doesn't give you any examples of iodide doing this, and not fluorine either. Biology will actually do this reaction with iodide as part of the biosynthesis of thyroid hormone, but I don't think we'll worry about that at this point. Maybe I'll show you some of it a little bit later. If you're going to do chlorine, the Lewis acid you use is FeCl3. A student will usually ask, could you use FeCl3 with Br2? Does it matter? The answer is I'm not sure, but the fact that they're giving you two examples where you've matched the identity of the group on iron with the identity of your electrophile maybe means it does matter. So, but I don't really necessarily have anything better to tell you than that. I'm certainly not going to give you options on a multiple choice exam where you'll have to distinguish between, whoa, which is the best one to use, this or that. That seems like a kind of a boring and cheap shot, so I'm not going to do that. Questions you want to ask about aryl halogenation? Yes?
The book has like two resonance structures having a positive charge all the way around the benzene. Do we need to worry about that?
Yes, that is an excellent final exam question. Which atoms share the positive charge in the ring? You should know it's 2, 4, and 6 for sure. I haven't drawn that resonance structure, but this is, and the intermediate here, though it's not aromatic, it is resonance stabilized. And where that positive charge is important. Okay, what else? Yeah?
Is there any regioselectivity?
Well, not for benzene in the sense that all of the carbons are identical, so it doesn't matter. Now, once something else is on there, it does matter. We'll talk about that. But it's going to depend on the identity of the group that's already there and not on the fact that we're adding chlorine or bromine. Yeah. Okay, what else? Okay. So reaction number 2, aryl is the word we use to describe a generic aromatic ring. So aryl nitration is nitration of an aromatic ring. We'll start with just benzene, and the conditions for this are nitric acid and sulfuric acid. Really friendly, happy conditions. You have to be very careful when working with nitric acid and sulfuric acid. A mixture of nitric acid and sulfuric acid is sometimes called aqua regia, and you can use it to dissolve gold. So, pretty caustic mixture of stuff. In any case, this installs a nitro group. And I'm not going to worry too much about, and I think your text may show this mechanism, I'm not going to worry too much about how to generate, I'll show you what the electrophile is, but I'm not going to show you how you take nitric acid and sulfuric acid and get this electrophile. We could do it, it just probably isn't worth the time. So when you add nitric acid to sulfuric acid, you can actually convert nitric acid into NO2 plus. And let's see. So if you want to know how that works, I'll just briefly talk you through it. Imagine sulfuric acid protonating the OH to turn it into a good leaving group. Then electrons kicking down from here, kicking off the OH, and you get NO2 plus. This is your electrophile in the nitration reaction. And so arrow pushing with that electrophile looks like this. Here's benzene. Attack the nitrogen. If I with the pi bond from benzene, if I stop there, I'd have too many bonds to nitrogen. So I'm basically going to treat the NO pi bond as though we're dealing with a carbonyl. So attack the nitrogen, break the nitrogen-oxygen bond, generate the following intermediate. Positive charge on the adjacent carbon. Some base, doesn't matter what it is. It could be water, it could be the conjugate base of sulfuric acid. Removes the proton to restore aromaticity and get us to our nitrated product, NO2. And again, you have this resonance stabilized non-aromatic intermediate where the positive charge is on carbons 2, 4, and 6. All right, anything you want to say about that? Okay, we're just going to push through the types of reactions that you can encounter in this chapter, and then we'll talk about what happens if you take a molecule that already has a functional group on it, like bromobenzene or nitrobenzene, and try to do a subsequent reaction on it. And how does the location of the nitro group or the bromo group influence subsequent reactions? That's the issue of regioselectivity. But before we do that, I just want to present some of the other reaction possibilities, okay? While we're on the subject, some of these functional groups are subject to further modification. So a nitro group can actually be converted into an amino group by reduction. So if you take and I'm not sure what to call this other than maybe we'll call it a derivatization reaction. We're changing the structure, we're making a derivative of nitrobenzene. You can take nitrobenzene and subject it to palladium catalyzed hydrogenation conditions or reduction conditions. You've seen this reagent used before to reduce a pi bond in an alkene down to the alkane. With nitro groups, it's possible to use these same conditions to reduce them to the corresponding amino group. And this will be really useful a little bit later. We haven't necessarily talked about this yet, but the nitro group is what we're going to call an electron withdrawing group because of resonance. Whereas, and I'll say more about that in a little bit, whereas the amino group is an electron donating group. Via resonance. And it's convenient whether or not the benzene ring has a withdrawing group or a donating group on it can influence subsequent reactions. So this switch from nitro to amino group is a convenient way to change the character of the benzene ring.
Is there a reverse reaction for that?
Not that I know of. Is there a reverse reaction for going from the amino group to the nitro group? Not really, not that I know of. So sometimes benzene rings with groups on them have non-systematic names. Nitrobenzene is good enough. You could call this aminobenzene, but almost any organic chemist will call it aniline, just because that's the non-systematic name. You don't need to know that, but I will occasionally refer to that molecule as an aniline out of habit, and so when I say that, you just need to understand what I'm talking about, and that's all. Okay, there's 2 or 3 other reactions to introduce new things on benzene rings. So let's do sulfonation. That sounds fun. This is installing a sulfonic acid group on a benzene ring. Sulfonation. The conditions for this involve SO3, which I don't actually know a lot about as a reagent, and sulfuric acid. Your electrophile is the protonated version of SO3. By the way, don't worry at all about sulfur having more than 4 bonds. Atoms that are lower than the second row of the periodic table are large enough to accommodate more than 4 bonds. We have pi electrons from benzene attacking the sulfur. We can then move those one or a pair of the electrons, we can move the electrons from a sulfur oxygen pi bond out onto one of the oxygens. That gets us the familiar intermediate in which we have a positive charge on the adjacent carbon. Again, you've got a resonance stabilized intermediate that is not aromatic. Then some base, we don't care what it is, probably the conjugate base of sulfuric acid, removes that proton to reestablish aromaticity. That proton is very acidic because its conjugate base is both neutral and aromatic. And of course, molecules that have very stable conjugate bases are highly acidic. Okay, so this installs a sulfonic acid group on the benzene ring. If you think that looks familiar, you've seen something like this before. You were introduced to an organic soluble version of sulfuric acid in 351, para-toluene sulfonic acid, TSOH. Okay, yeah, that's how you make it. Also, there are some soaps and detergents that you can make using this method. For example, one of the methods for making soap is to take a really long chain alkyl benzene and then using this. Now, I'm going to show you something that isn't going to make sense until we come back and talk about regioselectivity later. The sulfonic acid group ends up either here or, sorry, running out of page space. Or on the orthocarbon. Sorry, starting talking about stuff that I haven't explained yet. So when we talk about benzene rings that have multiple groups on them, we could refer to substitution patterns like 1,4 and 1,2 and 1,3, but more traditionally we say 1,4 substitution is called para, so this is the para product. 1,2 substitution is called ortho, that's the ortho product. 1,3 substitution would be called meta, the meta product. In this reaction, you tend to get only ortho and para products. That's not determined by these conditions, but it's rather determined by the nature of this alkyl group on the benzene ring, and we'll talk about that a little bit later. But if you look at the structure of the molecule that we've made, this is a strong acid, and so let me erase all of the labels. A strong acid in water would be deprotonated by water to generate the conjugate base and hydronium. And if you do that, you now have a polar head group and a non-polar tail, and there's your surfactant. We talked in 351 about making micelles out of things like this. And so that's an example of a soap that you can make. All right, sulfonation. Never mind on that. We've got two more reactions to do, introducing things on benzene rings. So we've done halogenation, nitration, sulfonation. The last two are versions of what are called Friedel-Crafts reactions, named after the German/French, I can't remember, chemist who discovered it. There are two of these. The first one is alkylation. That means installing an alkyl group on a benzene ring. And the alkylation reactions are very SN1-like. They involve electrophiles that are made from alkyl halides. So as an example, here is an alkyl chloride. Excuse me, as with the halogenation reaction, we need to add a Lewis acid to make the reaction go. So here's the alkyl chloride, here is the benzene ring nucleophile. The Lewis acid that we're going to choose is aluminum chloride. And again, is there some reason why you need to match the identity of the chloro group on your alkyl halide with the chloro group on your Lewis acid, aluminum chloride? Not sure, your text never explains it, probably. And so from a practical standpoint, that's why you'll see chloros in both places. What this does is it makes a new carbon-carbon bond between the benzene carbon and the carbon that used to have the halide in your alkyl halide. Mechanism for this reaction can be complicated. It honestly depends on the structure of the alkyl halide. So let me show you the one that seems to make the most sense, and there's evidence for this mechanism in the sense that there's evidence for a carbocationic intermediate. So you start with the alkyl halide, you add aluminum chloride to soup up the leaving group. Recall that aluminum, like boron, when it's bonded to three things, has an empty p orbital. So electrons from lone pairs on chlorine, HOMO attacks LUMO, are going to attack the empty orbital on aluminum to make the following intermediate. If Cl by itself was a good leaving group, then adding something to Cl that puts a positive charge on Cl is going to make it an even better leaving group. So we've used green for a leaving group that's good. We're also going to use orange to indicate that it's on fire. It's an extremely good leaving group. And so what will happen is the leaving group leaves to give you a carbocation. And then once you've generated that carbocation, that's a reactive enough electrophile for benzene to attack. So here's the carbocation. Pi electrons from benzene attack to create a new carbon-carbon bond. And this is the SN1 type step that I was talking about, losing the leaving group to get a carbocation. Your intermediate, again, will have a positive charge on one carbon. The adjacent carbon has what used to be the electrophile. Then a base, we don't care what it is, it could be Cl minus, comes in and removes the proton, thereby restoring aromaticity and giving you your alkyl benzene product. All right. So there are a lot of ways to generate carbocations, and you will see some examples in your text where you do a similar reaction, but instead of with the alkyl halide, the alcohol and perhaps a strong acid like H2SO4. And that will work too. Now when you see that, you're going to be tempted as what on earth is going on? You've totally changed the reagents. That's where you have to relax your eyes and see connections, right? The key point of this reaction is a benzene attacks a carbocation. So you should look at that and see in your mind's eye from 351, oh, alcohol under strongly acidic conditions, I know what to do there. Protonate the alcohol to turn it into a good leaving group leaves to give me a carbocation. From that point on, it's exactly the same as the Friedel-Crafts reaction. So don't be distracted by the additional details. The real feature of the Friedel-Crafts reaction is not necessarily how you generate the carbocation, but that once you generate it, benzene can attack it. Okay? Yes?
So we have to worry about carbocation rearrangement, not in this one because it's
Sure.
related, but
Yeah, do you have to worry about carbocation rearrangement? Yes. In the sense that that's evidence that there is a carbocation here because they have observed carbocation rearrangement for this reaction. Now, there's a whole rabbit hole that your text at least used to take you down related to the fact that you could get rearrangement products. I suppose that I'm not going to ask you to predict rearranged products for the Friedel-Crafts reaction. However, if you were to be given something like this, you would perhaps not be surprised to see, in addition to the expected product, a rearranged one. So rearrangements are possible because of the carbocation. I would say don't worry about predicting the rearrangements, but if they happen, could you explain them in a mechanism? Okay. It gets worse than that. There's evidence that, I mean, you can do the reaction alkyl benzene, you can generate alkyl benzenes even with primary alkyl halides where you would worry that primary carbocations aren't good intermediates, and they're generally not. And so the mechanism for this reaction probably has to be SN1-like, or sorry, SN2-like. That is, you generate the electrophile as we talked about previously, and then probably the benzene ring pi electrons attack at the carbon as the leaving group is leaving, sort of in an SN2-like step. So that's fine. There's sorry. And then the second step is the same, restoring aromaticity. Your text points out that if you add additional groups beyond this ethyl halide, like if we put other things, there's actually allowed rearrangements where some of these carbons are going to end up on that primary carbon for reasons that I'm not sure, other than that they avoid the potential for a primary carbocation. We're going to pretend like all of that stuff doesn't exist. So we're going to pretend, pretend like you can use, this reaction definitely works for ethyl halide. I think your text at least used to, in an earlier edition, say that if you have additional R groups beyond the ethyl halide, that you can get some rearranged products as well. Not only the linear one, but also, and this is horrific, this one. We're going to pretend like that doesn't exist. So if you use a secondary or tertiary alkyl halide, the mechanism involves a carbocationic intermediate. If you use a primary alkyl halide, the mechanism is SN2-like, no carbocation, and we're going to pretend like the rearrangement doesn't happen. Okay? I'm sorry for talking about something that isn't going to happen. I probably should have just skipped over that entirely. I was afraid one of you was going to read about it in the text and say, well, what about? And so I wanted to prevent that. But maybe you weren't worried about it in the first place. So, okay, let's talk about a derivatization reaction you can do with an alkyl benzene. To convert an alkyl benzene into something else. So let's just use this reaction where we've installed an alkyl group. If you then use a reaction from chapter, whatever it was on radicals that we did in 351, remember that bromination is selective for the more stable radical. So of all the carbon-hydrogen bonds present in this alkyl benzene, where is the most stable radical? Is it here on the benzene ring like that? No. That? No. That one? No. Yes, it is that one. Why is it that one? So more, you can think about radical stability in the same way that you think about carbocation stability. Radicals are generally electron deficient species. So more substituted radicals are more stable. Also, resonance can stabilize radicals. So if you generate a bromine radical, you can abstract a hydrogen atom to generate a radical intermediate that looks like this. Not only is that more substituted, but it's also stabilized by resonance. Final exam question: which atoms in the benzene ring share the radical? I'm going to rely on you to push arrows to draw the resonance structures that would demonstrate that. Once you get that, this is called a benzylic radical. The carbon that is adjacent to the benzene ring is called, in general, the benzylic carbon. At least you won't hear that too much, but I may occasionally say it. Once you make that, and that is the more stable radical of the other options. Once you have that radical, you can do the bromination reaction that you saw at the end of 351, where we make a new carbon-bromine bond. All right? And then, now that you've got that alkyl halide there, you have a lot of different options. You could do substitution chemistry sort of any way you want with that alkyl halide. You could replace it with many different things. Any nucleophile that you might come up with. You could also do an elimination reaction to put a pi bond in place. And this is actually a molecule called styrene, which is a precursor to the polymer polystyrene. All right, so that's one derivatization reaction. Radical halogenation at the benzylic carbon. The second one is sort of we're not going to show you the mechanism of it. It's sort of a wacky Thor's hammer type reaction. You use potassium permanganate, which is a really strong oxidizing agent. And this reaction requires, as a prerequisite, at least one benzylic CH bond. Again, we're not going to worry about the mechanism. If you have at least one benzylic CH bond, this KMNO4 mechanism breaks all of the bonds between the benzylic carbon and its substituents, but as I said, one of them has to be, at least one of them has to be a proton, and it replaces them all with carbon-oxygen bonds. So it's kind of magic as far as we're concerned. There is a mechanism, we're not worrying about it, but this will convert an alkyl group into a carboxylic acid. This is another, remember back when we talked about nitrobenzene, we had a reaction where you could convert an electron withdrawing nitro group into an electron donating amino group. We're going to see in the second half of today that an alkyl group is an electron donating group via not resonance but an inductive effect, whereas we're going to see that a carboxylic acid is an electron withdrawing group via resonance effect. And so this derivatization reaction changes something from a donating group to a withdrawing group, and so it has the potential to be strategically useful. All right. Strategery, yeah, yes.
Should that say carbon-carbon bond?
No, it needs at least one benzylic CH bond. Yeah, that's the, and I don't know why, but your text points out, basically this doesn't work on the T-butyl benzene. So if those were all methyl groups, the reaction wouldn't work. I don't know why.
What does happen to that methyl group?
My guess is you lose it as either CO2 or perhaps formic acid or something like that. Don't know. Good question. There are some reactions that are useful enough, but the mechanism is complicated enough that it's not worth knowing at an introductory level, and this is probably why. This is one of these. Your text, I think, is showing you this because you can use it to simply switch from a donating group to a withdrawing group. You're going to see reasons for doing that very soon. Mechanistically, though, it's complicated enough that it's not worth knowing or worrying about. All right. Other questions about the Friedel-Crafts alkylation? Okay, well, last new addition of something to a benzene ring reaction is called Friedel-Crafts acylation. Acylation differs from alkylation. An alkyl group is this, an acyl group is this. In other words, an acyl group is a carbonyl that gets attached to something else. So the Friedel-Crafts acylation reaction looks like this. You start with benzene, but instead of using, and you're still going to use aluminum chloride as a Lewis acid, but instead of using an alkyl chloride, we're going to use an acid chloride, which is some R group, a carbonyl, and then Cl. And this reaction makes a new bond between benzene and the carbonyl carbon of the acid chloride. And so conceptually, I think you can imagine what's going on here. We're using the Lewis acid to turn chloro into an even better leaving group. So here's what your text, I think, shows as the mechanism for this reaction. Lone pairs on chloro attack aluminum. It's a fair question as to why the lone pairs on chloro attack aluminum instead of the lone pairs on oxygen. I don't have a good answer for that. But as before, you turn what used to be a good leaving group into an on fire leaving group. In fact, it's such a good leaving group that it can just leave. The way I'm going to show this happening is lone pair electrons on the oxygen kick down and leaving group leaves. That should look vaguely familiar to some of the carbonyl chemistry you've already known. But if that happens, if those lone pairs kick down and the leaving group leaves, notice now that the carbonyl carbon has to be sp hybridized, because now it's only bonded to two things. Okay. Notice that this group here is resonance stabilized. I could put a positive charge on the carbon or on the oxygen. And this intermediate is called an acylium ion. It's a resonance stabilized carbocation. And it's electrophilic at the carbonyl carbon. So now benzene, the mechanism will be exactly what you would predict. You can draw the mechanism using either of the resonance structures for the acylium ion. I'm gonna just use the simplest one. Attack the carbon, the positively charged carbon, get an intermediate where we have destroyed aromaticity, but the positive charge is still stabilized by resonance. Then some base, we don't care what it is, could be Cl minus, comes in, removes the proton and restores aromaticity to give you your acyl benzene product, or an acylated product. Okay. Questions about that? Yeah.
Quick, it's just this trend that when you benzene ring attack something, there's a positive charge. Is it ever reasonable to just add something else and like have that attack the positive charge? So you can add two things at the same time to the benzene ring.
Add two things at the same. Oh, could you then have something else attack here?
Yeah.
Good question. The answer is no, because this intermediate is high in energy. It doesn't last a long time. If you were to look at the energy diagram for this reaction, it would be very much like an SN1 reaction. Benzene attacks to lose aromaticity, that's the slow step, and then the second step is downhill. So that intermediate's not really around long enough for other things to happen. And the fact that usually acid-base reactions, losing a proton is actually quite fast. And that's why with benzene we see substitution products rather than addition products. All right. One last derivatization reaction on acyl benzenes. Notice that derivatization reaction. We will talk about why this is the case, but notice that an acyl benzene is, the carbonyl group is an electron withdrawing group via resonance. There we go. The reaction I'm going to show you now reduces the ketone all the way down to the alkane. Now you know how to reduce ketones to alcohols. That's lithium aluminum hydride or sodium borohydride. But I don't think I've ever shown you a reaction that will take the ketone and turn it just into an alkyl group that will replace each of the carbon oxygen bonds in the ketone with a carbon hydrogen bond. Converting acyl to alkyl turns something from an electron withdrawing group by resonance to an electron donating group via an inductive effect. We'll talk about that again in just a little bit. The conditions for this reaction involve some unusual reagents you haven't seen before. Hydrazine, hydroxide. If hydroxide's present, it almost always means water is present as well. Your text presents two different reaction conditions that do this. One is listed here. The other involves a mixture of zinc and mercury. We're not going to worry about the metal-related one. We'll do just the hydrazine-based reduction. This mechanism is known, but you don't have to know it. It's not hard. It's kind of cute. It involves expulsion of nitrogen from the molecule. I'm dying to tell you, but I probably will restrain myself because you've got enough to worry about with the test tomorrow. But if you want to know more, look it up. It's fun. Seriously. All right. So to review what we've done, oh, sorry. Any questions about acyl, fatal craps acylation? Everything we've done this hour has been about adding one thing to a benzene ring and then perhaps tweaking its structure afterwards. We've learned to add halogens to a benzene ring, aryl halogenation. Nothing you can do with the halogen once it's there, so there's no derivatization reactions to worry about. We learned about adding a nitro group to a benzene ring, and then we learned a cute little derivatization reaction where you can convert the nitro into the aniline, and that's using hydrogen and palladium on carbon. This converts a withdrawing group to a donating group, and that has consequences that we'll explore in the next hour. We learned how to add a sulfonate group to a benzene ring. No derivatization reaction there. I will just say that this is a nice way of making soap. I should point out while we're here that the sulfonate group is an electron withdrawing group via resonance, and we'll say more about that a little bit. We learned how to do alkyl groups via the Friedel-Crafts reaction. An alkyl group is an electron donating group via an inductive effect. We can derivatize the alkyl group either by radical halogenation at the benzylic carbon or sort of Thor's hammer oxidation of the benzylic carbon all the way up to the benzoic acid. That's what this is called. Again, the radical halogenation was a way we can convert the alkyl benzene into something with a good leaving group on it, and then we can do any number of things to that good leaving group. The KMNO4 oxidation was a way of converting a donating group into a withdrawing group. That will become useful in a little bit. We talked then about acylation, where we install the acyl group, and we have a derivatization reaction there of reducing the acyl group down to an alkyl group, thereby converting a withdrawing group into a donating group. So those are your tools. Now we need to start talking about what happens when I want to do one of these reactions on a benzene ring that already has something. And that's where we get to the issue of regioselectivity. It's fun and predictable, but you got to know what a donating group and a withdrawing group is. And so that's where we're going next. So let's take a break for a few minutes. We'll talk about donating, withdrawing groups and regioselectivities, and then we'll practice. All right, so the issue of regioselectivity wasn't an issue before because all of the carbons of benzene are identical. But once you have one or more groups on the benzene ring, that situation changes. So as an example, suppose that we already start with nitrobenzene and we want to do a chlorination reaction. Aryl chlorination, FeCl3 and Cl2. There are, let's see, 4 different carbons now in benzene. Carbons 3 and 5 are identical, and carbons 2 and 6 are identical. Relative to the nitro group, we're going to call carbons 2 and 6 the ortho position. Carbons 3 and 5 we'll call the meta position, and carbon 4 we'll call the para position. And so there's basically 3 places a chloro group can go. You could have chloro on the ortho carbon, on the metacarbon, or on the paracarbon. Just as an aside, why didn't I put the option where chloro was on carbon 1? Well, we could do that, right? You could do the intermediate that would look like this. But is there any proton to remove to restore aromaticity? Nah, you're kind of, yeah. So this is not particularly important, but you'll hear some organic chemists call carbon 1 the ipso carbon. And there is no ipso substitution, because if you do that, you can't restore aromaticity. You have to have at least on the carbon that gets the new group, there has to be a proton so that you can remove it in the second step and restore aromaticity. All right. So that's why we only have the ortho product, the meta product, and the para product. Of these three options, we only observe for this reaction the meta product. Okay? In contrast, if we were to instead start with the chloro group and do the nitration reaction subsequently, our options are still the same three molecules. I guess I'll draw them this way. Ortho, meta, and para. For chloro, we only observe ortho or para substitution. Okay, so there's a difference. Yeah.
With everything where we do order, will between the two reactions, will it always produce all three, O and P? So right now we're doing nitro and chloro. If we decide to do acyl and chloro or whatever.
So I guess to answer, I'm a little bit.
I'm trying to.
I guess no. With the nitro group, you only see the meta option.
Right, but between the two, if I start with a nitrobenzene and do chloro, I'm going to get meta.
Right.
If I start with a chlorobenzene and do nitro, I'm going to get
Ortho and para.
Will the set where I'm doing chloro and nitro, the two ways, always produce all three when I go to different sets?
I don't think there's a hard and fast rule the way you're looking for it. It actually has to do with the character of the group that's already there. We've said before that a nitro group is an electron withdrawing group by resonance. And it turns out that by virtue of the lone pairs on the chloro is an electron donating group by resonance. And that influences regioselectivity. We will see that electron donating groups by resonance always prefer ortho and para substitution. And electron withdrawing groups by resonance always prefer meta substitution. And we're about to explain why. And it has to do with that final exam question I keep telling you I'm going to ask you, which is which carbons have the positive charge? All right, so let's dig in and try to figure out why and what's going on here. And to do this, we're going to think about the intermediate, the carbocationic intermediate that precedes each of these options. We're going to start with the nitrobenzene adding the chloro and see whether we can discern differences in the stabilities of the potential carbocationic intermediates. Okay? So, let's imagine the nitro group is already on, and let's imagine that we add the chloro to the ortho carbon. Such that the positive charge is there. And again, we can number the atoms if that would be useful. Remember, we're using the terms ortho to refer to carbons 2 and 6, meta to 3 and 5, para to carbon 3. So this is if we put the chloro, this is the intermediate that we get, the carbocationic intermediate that we get if we put the chloro group on the ortho carbon. Let's do the same for the meta position. And then let's do the same for putting the chloro at the para position. Okay. Now, we're going to draw some resonance structures here. Showing where that positive charge can be. If you have trouble converting from one resonance structure to another, you should practice that. Simply, for positive charge situations, you simply move the pi bond over from 5 and 4 to be between 3 and 4, and then a positive charge is left behind on 5. Okay? Oops, I'm missing those groups. And then I suppose we could also draw this resonance structure. Okay. That demonstrates that that positive charge is on carbons 3, 5, and 1. Okay. Now, I'm not going to draw out the resonance structures for the meta and para carbocations, but I am going to use blue to highlight where the positive charge can be. For the meta substitution, the positive charge is on 2, 4, and 6. For para substitution, the positive charge is again on 3, 5, and 1. All right. Which of those situations do you think is better? To answer that, you may need to know a little bit more about the nitro group. And so it might be worthwhile to draw out the Lewis structure of the nitro group. And maybe let's do that here. Okay. So, if you had to pick, which carbocation is more stable, the ortho, the meta, or the para? Meta. Why is that better than the other options? Right. In ortho and para, you have the positive charge in the carbocation is on carbons 1, 3, and 5. That's exactly where, if it's on carbon 1, that's exactly adjacent to the nitro group, which has a positive charge on it. Right? So that's destabilizing. You could think of it as charge repulsion. So, and the same thing for the para-substituted carbocation. the positive charge is again adjacent to that nitro group, which has the positive charge on it. Meta, well, at least the positive charge is not adjacent, right? So you can rationalize the regioselectivity of the reaction for adding the chloro to the nitrobenzene by saying that the pathway to meta substitution passes through a lower energy carbocation and is therefore faster. So if this is our energy diagram for meta substitution, what we're saying is that ortho and para substitution go through a higher carbocationic intermediate, and so it's faster to go through meta. Okay? That's one way of understanding the regioselectivity for adding the chlorination to the nitro. There's a second way of understanding this, and that is to just say that if you look at nitrobenzene itself, even before we make the carbocationic intermediate, nitrobenzene has a characteristic that is common to all electron withdrawing groups via resonance, and that is you have on the atom that's attached to the benzene ring, you have a pi bond to an electronegative heteroatom. And whenever you have that situation, it's going to be possible for you to draw a resonance structure in which you pull electron density from the benzene ring out onto that adjacent electronegative heteroatom, thereby putting the positive charge in the benzene ring. Final exam question. Which carbons share that positive charge? 2, 4, and 6. All right? I can't count. Where did 3 go? So you could infer that nitrobenzene automatically makes 2, 4, and 6 more electron poor than 3 and 5. Okay, so from benzene as a nucleophile point of view, carbons 2, 4, and 6 are already deactivated. They already have a substantial amount of positive charge on them. So it makes sense that carbons 3 and 5 would be more reactive. So that's another way you can look at it. 2 alternative views. One is to focus on where the electron-rich portions of the benzene ring starting material are. The second is to focus on where the carbocation is most stable in the activated positively charged intermediate. 2 sides to the same coin. Doesn't matter which one you pick, it'll give you the right answer either way. Okay? All right, now let's talk about why. Anything you want to ask about that? That trend is general for electron withdrawing groups by resonance. Okay, and we'll talk about what those are, just review what those are in just a little bit. But you can mix and match all day long. But if you know that something is an electron withdrawing group by resonance, that tells you that carbons 3 and 5 are going to be where the substitution product is going to happen. You're going to get meta substitution. Okay, let's do the chloro group. Same approach. Let's look at the stability of the carbocationic intermediate. Again, we'll do ortho, meta, and para. This time we won't draw resonance structures because you've hopefully gotten better at figuring that out. So ortho substitution with the nitro group would give us this intermediate. Meta substitutions from chlorobenzene with the nitro group would give us, this intermediate, and then para substitution would give us this one. Except I'm forgetting positive charges. Now, which atoms share the positive charge? For the ortho, substituted carbocation, it's 3, 5, and 1. Same thing for the para substituted carbocation. For the meta substituted carbon, it's 2, 4, and 6. Now, can you see any reason why having the positive charge at 1, 3, and 5 may be better than having it at 2, 4, and 6?
Chlorine can help out.
Chlorine can help out how?
Dump the electrons in there.
Okay, so you've got a resonance structure that, for the ortho substituted pattern where the positive charge is adjacent to the chloro. Hold on, I thought chlorine was electronegative. Shouldn't that be bad? It is electronegative, but like oxygen and other electronegative heteroatoms with lone pairs, it can donate, those lone pairs can stabilize the positive charge via resonance, okay? So I could draw a resonance structure in which chloro further delocalizes the positive charge, and that is always a stabilizing effect. That resonance structure should look weird to you. You're not used to seeing chloro with a positive charge on it. It's not a great one, but it is stabilizing because you're spreading out the positive charge. And so yes, it is lower in energy. The carbocations where the positive charge is on atoms 1, 3, and 5, those carbocations are more stable than when it's on 2, 4, and 6, because at least when it's on 1, 3, and 5, you can spread out electron density onto the chlorine ring. Chlorine donates its lone pairs in there. Okay? So that's same explanation as we saw before with the nitro group, only because chloro is a donating group rather than a withdrawing group, ortho and para become more stable rather than less stable. All right? Okay. So, and this is general. In general, donating groups are going to favor ortho and para substitution because ortho and para substituted carbocations place positive charge adjacent to the donating group, where they can stabilize it either by resonance or by an inductive effect. Okay, questions so far? Yeah.
Does it change if you add an electron donating group to a benzene that already has an electron donating group?
Does it change if you add a donating group to? I'm not sure. Are you asking what if I have a benzene ring with 2 donating groups? What then?
Yeah, like if you have that benzene ring with the chlorine, and then you try to add another chlorine, does that change anything? Sorry for that.
No. It's a good question. In general, the regioselectivity is governed by the things that are already there, not the thing you're installing. Though if you go on to do subsequent reactions, then you've got to take multiple things into account, and we'll talk about that. All right, let's just review what a donating group is versus what a withdrawing group is. Your text talks about 2 major issues here. The first is regioselectivity, which is the one we're going to focus on. The second is whether the substituted benzene reacts faster than benzene or slower than benzene. That's less of an important issue for what we want to do. I might say something a little bit about it. Donating versus withdrawing. And then we'll put regio selectivity here. I'm going to rank these in terms of their ability to donate. So we're going to start out with, and the squiggly line represents, that's where we're attaching to the benzene ring. NH2, and this can also include NHR and NR2, where R is some alkyl group, not a carbonyl and not a benzene ring. If you do something that can interact with these lone pairs on the nitrogen, that can change how well of a donating group it is. This is a donating group via resonance. And therefore, its regioselectivity is for ortho and para substitution. Let me back up and just say that as we saw with the chlorobenzene, we got a mixture of ortho and para products. I didn't say what the relative percentage of ortho and para products would be. You might predict that para would be favored by sterics, by keeping the groups farther apart from each other. In general, we're not going to worry about trying to bias the system to give us major ortho versus para. We're going to assume that if you get a mixture of ortho and para, you could separate them and take on the desired molecule in subsequent synthetic steps. What we're not going to allow is if you want to use a meta-substituted product, but you make ortho and para. We're not going to say, oh, you get to find the small, minuscule amount of meta-substituted product that's present. No, you gotta, it's okay to use either ortho or para in subsequent synthetic steps when you get a mixture of the two. It's not okay to get ortho and para as majority products and then pretend that you actually made the meta product. Does that make sense? You gotta control the regioselectivity as best you can. All right. So the aniline groups, the ones that have amines, are those are electron donating groups via resonance. The pattern really is a heteroatom with a lone pair on it can be a donating group via resonance. Also, just a little bit less good is having an OH group, that's called a phenol, or having an OR group, where again, R is alkyl, that's called an anisole, and that doesn't matter. I guess I'm just flexing, so sorry about that. I need to stop being so self-indulgent. It's an electron withdrawing group via resonance. Sorry, electron donating group via resonance. Again, you have lone pairs on a heteroatom adjacent to the benzene ring, and that's an ortho and para director. Now, still ortho and para director, but not quite as donating as the anilines or the phenols, is where you take the aniline or phenol nitrogen and you attach it to a carbonyl group. Notice that this is not attaching the carbonyl carbon directly to the benzene ring. This is attaching the heteroatom, the nitrogen or the oxygen, to the benzene ring. These are still electron donating groups via resonance, but they're not quite as good of a donating group as are just the straight up OH, OR, or NH type groups. Why do you think that is? Any explanation for why those are not quite as good? Go ahead.
The oxygen, the carbonyl
right, the carbonyl oxygen actually can suck electron density away towards itself. So you've sort of got a bit of a tug of war, and therefore the lone pairs on the oxygen are not as good at donating into the benzene ring.
But they still do it.
They still do it, and they'll still be ortho and para directors. That's a key mistake that some students make. They will see something like this. Ooh, we're drawing it in red because it's wrong. Does that make you feel a little nervous? Some students will see this, and they will say, oh, I remember carbonyls are electron withdrawing groups. Therefore, this should be ortho, this should be meta substitution when they do a reaction. And they'll misunderstand. These are two different situations, right? Here, the oxygen for the ester is adjacent to the ring. It can still donate electron density in, though not as effectively as if the lone pair were entirely localized on that oxygen. In contrast, over here on the right, the ester oxygen lone pairs are not adjacent to the benzene ring. The thing that dominates is going to be the carbonyl, which is a withdrawing group, right? Donating group, withdrawing group. It depends on, so it's, you can't memorize esters are donating groups, esters are withdrawing groups. You have to pay attention to how it's connected to the benzene ring. All right. Okay, now slightly not as effective as the donating groups, but still ortho and para directing in terms of regioselectivity are the alkyl groups. So doesn't matter whether it's primary or secondary or so on. These are all electron donating groups via not resonance, but what's called an inductive effect. What we mean by this, and let me just draw the carbocationic intermediate. We'll draw the one for, say, ortho substitution. Here's your electrophile. Remember, the positive charge is on 1, 3, and 5 when we do ortho substitution. An sp3 hybridized carbon is less electronegative than an sp2 carbon, and that means that the sp3 carbon is willing to give some of its electron density away to the electron poor sp2 carbon. So it's a donating group by virtue of being less electronegative than a benzene carbon. And so you can imagine it's favorable to have the positive charge adjacent to the alkyl group, because the alkyl group is going to play friendly and share electron density. Okay. And then sort of lastly on our list of donors, you've got halides like Br and Cl. These are electron donating groups via resonance, and they are also ortho and para directors for reasons that we've talked about. They're not as good of donors as oxygen and nitrogen, mostly because of their size and bond length. Carbon, bromine, carbon, chlorine bonds are longer than carbon, nitrogen, carbon, oxygen bonds. The resonance donating effect depends on the resonance donating effect is more favorable when the heteroatom can get closer to the benzene ring, and also when, if you look, bromine and chlorine are from different rows of the periodic table, as is carbon. And that means their orbitals on bromine and chlorine are larger and more diffuse, and they don't overlap quite as well with carbon as do orbitals on oxygen and nitrogen. So it's easier to do resonance and conjugation between oxygen and carbon or nitrogen and carbon than it is between bromine and carbon or chlorine and carbon. All right. So all of those are ortho and para directors. Yeah.
It says that bromine and chlorine deactivate the benzene
Yes, that's entirely different from regioselectivity. So the issue of activating versus deactivating, and I can't spell, deactivating, is an issue of kinetics, that is speed of the reaction relative to benzene. So, oops, and that's terrible penmanship. So up till this point, all of these things are faster than benzene with speed increasing. For the halides, they react slower than benzene. And that is because the resonance effect dominates regioselectivity. But for a lot of these resonance donors, there's another thing going on in the background, and that is electronegativity. And a lot of these groups that are donating groups via resonance are electron withdrawing groups via electronegativity, meaning you're adding something to the benzene ring that is more electronegative than carbon. So the lone pairs are donating into the ring, but the group is pulling through the sigma bonds. And it's tough to rationalize what the trade-off should be. And so what we're telling you is electronegativity starts to win for the halides. Now, that's not going to affect your decision for regioselectivity, and it's really only a practical issue. If you're doing this in the lab, you want to be prepared this reaction might be a little bit slower.
So it can be deactivated, but it can be electron donated.
Via resonance, yeah.
So, but also the book says that halogens are electron withdrawing groups.
They are or they aren't?
It says they are.
Right. All of these have dual character, okay? The anilines, the phenols are donating groups via resonance, but they're withdrawing groups because of electronegativity.
Okay.
Now,
The resonance.
for it, there's a trade-off because for the nitrogens and the oxygens, donating group wins for regioselectivity and it wins for reactivity relative to benzene. For whatever reason, for chloro, donating group wins for regioselectivity but loses for reactivity relative to benzene.
I see. Okay.
Yeah.
Okay, so here we're just talking about regioselectivity.
That's right. Our focus is going to be on regioselectivity. I really am not going to ask any questions, is this activated or deactivated relative to benzene? It's okay and you can figure it out, but we don't have a lot of time for stuff like that. There is a trade-off and it's hard to predict, and at best you're just going to memorize it. So if you're going to be memorizing anyway, I would rather you focus on the regioselectivity issues than the speed relative to the benzene ring.
Okay.
Yeah. Okay? So your text will talk about this, and that's fine. Just see it in terms of a trade-off of as donating ability decreases, electronegativity starts to win. Yeah. All right. Yes?
Should we be understanding why the ones at the top are better than the ones at the bottom?
Should you be able to understand why the ones at the top are better than the ones at the bottom? Yes, and I'll show you how. First, notice the nitrogen donating groups are better than the oxygens. That's a pure electronegativity argument. Nitrogen's less electronegative than oxygen. These ones are worse than these ones. Why? Because of the reasons we talked about with the carbonyl group. Resonance is a more powerful effect than alkyl donation. And then finally, why are these better donors up here than these? That's a difference in size and orbital overlap. The ability of these large groups to get close into carbon decreases their ability to donate. Yeah. Okay. We need to talk about the withdrawing groups quick, and then I want to do some examples. The withdrawing groups we don't necessarily need to rank in terms of their ability to to deactivate the benzene ring or activate it relative to benzene. I'm going to write them here in order of their withdrawing ability. They are all electron withdrawing groups via resonance. The dividing line here is between ortho and para versus meta directors. You've got your carbonyl groups and your aldehydes, your ketones, carboxylic acids, esters, anything where the carbonyl group is directly attached to the benzene ring. Behold and do not be deceived. This arrangement is different from this one. The carbonyl group is attached to the benzene ring here. That's a withdrawing situation. If the nitrogen or the oxygen are attached to the benzene ring, that's a different situation. Some of you will make this mistake on an exam. You will come to me and say, you said in class that amides and esters are electron donating groups by resonance. Therefore, in my thought process, I thought they would be ortho and meta directors. And I will say, let's look at the video. Let's go back. Let's see the instant replay on what was actually said in class. No, sorry. I will tell you, pay attention to where the group is attached. It's different if it's attached to the carbonyl versus the nitrogen and the oxygen. The sulfur group fits the pattern of an electron withdrawing group via resonance. You have a double bond or a pi bond to an electronegative heteroatom adjacent to the ring. You can use it in much the same way as you can use a nitro group. These are all electron withdrawing groups via resonance, and they are all meta directors. Incidentally, they are all slower than benzene. And if we wanted to split hairs about it, we could say that the nitro group is a better withdrawing group than the ketone, though why that's the case, I think, is empirical, so we won't worry about this relative ordering of the withdrawing groups. Okay, so now we need to practice, and we're not just going to do mono-substituted benzenes. Let's do di-substituted benzenes and more. Let's do a synthesis. So suppose I start with methoxybenzene, and I wish to make CH3Cl. Sorry, I wish to make this molecule where I have, in addition to the methoxy group, I have the methyl group and the chloro group. What do you think I ought to do? So yeah, let's see what we can come up with here. If I were to add, option one is you want to add the methyl group first. That's Friedel-Crafts alkylation. I'm going to get a mixture of ortho and para products. That's the best I can do, so I'm just going to add plus the para isomer. Now, at this stage where I want to now add the chloro group, methoxy is going to prefer substitution ortho and para to it. Methyl is going to prefer substitution ortho and para to it. You've got opposition between two donating groups, but we've just learned that the methoxy group is a better donor than a methyl group. Therefore, the better donor wins by affecting the reaction. When two donating groups oppose each other's regioselectivity, the more effective donating group wins. Okay? So you do want to be familiar with this ranking order, this list, so that you can make good choices. It's okay, we're in a situation where methoxy and methyl oppose each other, because we can reasonably suspect that methoxy's preferences would win, and we could get that product, okay? Would there have been anything wrong with doing chloro first? I don't really think so, actually. If we had, if we instead had added chloro first, we could have gotten the chloro product plus the ortho isomer, which we're going to separate and not worry about. Methoxy, again, is going to prefer ortho and para to it, but of course this para position is ipso relative to the chlorine. There's no proton to be removed, so we can't substitute there. Chloro is going to prefer ortho and para to itself. Same issue with the ipso carbon. Again, two opposing donating groups, the better donor dominates regioselectivity. So we could reasonably expect that when we do the Friedel-Crafts alkylation reaction, we could get the methyl group on that adjacent carbon. Okay, questions? Yeah.
And it would be just as reasonable as well. Like we get the other product of this too. Like you could have all three on the top there. You could have the OME on the top middle and the CH3 on the right and the Cl on the left. Is that fine too?
Sorry, left, right.
Just yeah, the top three carbons. You could have all of them attached to there, right? Because it'd be like the same issue.
If you use the ortho isomer and then push down through the Friedel-Crafts, you could have carbon 1, 2, and 6 with our substitute.
So you're thinking about, could you make, if you had desired, could you have made this one?
Or not even could you, like wouldn't it automatically make that if you were to do these steps?
If you separated out the ortho isomer and just did the reaction on this one, then no.
Oh, okay,
Yeah. There are some subtleties that you probably don't need to know that I think we're not going to worry about. Let's see if I can find some synthesis problems from your text for us to practice on. I recommend that you spend some time on this, just because there's one or two synthesis problems on this exam that relate to this kind of stuff. Go ahead.
So in case that we have two electron withdrawing groups, is the hierarchy the same where the ones at the top are stronger than the ones at the bottom are weaker? The ones at the top eight, as shown in
Withdrawing groups? Okay.
with two withdrawing
Yeah, so let me tell you, if the situation you're going to be dealing with is if two donating groups oppose each other. Your text, as I recall, doesn't give you a lot of tools for what happens if the two withdrawing groups oppose each other, or if a donating group opposes a withdrawing group. So if you find yourself in that situation with problems that I give you, there was a better way that would have avoided that. Yeah. Let me just see if I can think of an example that would give us a chance to think about those issues. Synthesis, substitution effects. Sorry. Okay. Sure. This one's fun. Okay. Let's think strategically. You've got a donating group here, an electron donating group via resonance here, and an electron withdrawing group here. And the substitution pattern is all meta. That should make you uncomfortable, right? Because if I added one of these donating groups first, there's no way the other groups could be meta. So I want to start using my derivatization reactions to think, could any of these groups have previously been something that was withdrawing? Right? Because if we do the hydrogen and palladium on carbon, then that could have been a nitro group. Okay. Does it get easier from that point? Which one of these should I put on first? Certainly not the bromine, right? That's an orthopara director. We don't have any orthopara substitution. So that one's going to go on last. Does it matter, the nitro versus the Friedel-Crafts group? Yes. Yes or no?
Yes.
Why do you say yes? Friedel-Crafts, both of these are electron withdrawing groups via resonance. So from what we've learned so far, either of them could go first. Now, there is a detail in your text that Friedel-Crafts doesn't work very well on already deactivated benzene rings, but I give you permission to pretend like that detail does not exist. Okay? Ooh, I should have made this harder. Oh well. Okay, fine. We're out of time, so I want you to go ahead and plot out the synthesis on that one. I'll write it in the notes. I want you to see how this problem could have been even more difficult had I written it this way. Because then you would have needed to know you could have had that be a nitro group, and you would have needed to know via a derivatization reaction that that could have been a ketone. Okay, practice, practice, practice.